This section 3.8 is the last section for chapter 3. We're going to determine whether quantified arguments are valid or invalid by using what we call Euler diagrams. And these are a way to use pictures to determine whether an argument is valid or invalid. And again, we're only using these for quantified arguments. The reason being that quantified arguments, so these 4 examples, we have an all are, no are, some are not. These are quantified statements. And oftentimes it's difficult to write our conditional statement and use a truth table when determining whether quantified arguments are valid or invalid. So let's look at these diagrams. This first diagram represents all A are B. So when we talk about A, that's going to be this set. So we use a circle to represent all the things in set A. So all A are B means that everything in set A is inside of set B. So A is inside set B. Now that second diagram, no A are B, means the set of all things in A are not in the set B, so these two sets are completely separate. They don't overlap in any way. These last two, the first one is some A are B. So when we say some A, remember some is at least one. So at least one thing in A is also in set B. This dot represents an element of set A that's also in set B. So the circles are sets of things. The dots represent one thing. So this says there's at least one thing in A and also in B. The last diagram would be some A are not B. That says it exists at least one thing in set A that's not in set B. So I can write a dot to represent that thing in A that's not in set B. So these are the 4 possibilities when we look at a quantified statement. The process of determining whether a quantified statement is valid or invalid is given in this box. So the first step is we're going to choose one of those 4 diagrams to draw our first premise. And then in the second step, we're going to take our second premise and we're going to draw a diagram on top of the first premise. So our argument is valid if every diagram supports the conclusion. So if every possible diagram supports our conclusion or makes a conclusion true, then the argument is valid. However, it's invalid if we can come up with at least one diagram that does not support the conclusion. In the previous section, we used truth tables to determine whether an argument was valid or invalid. So remember, if we had all true, the argument was valid. So that's similar here to every diagram true, the argument is valid. If we have it, if we can find one diagram that makes a conclusion false, then it's invalid. So again, this is just a lot of words. It's usually easiest to see if we just go ahead and go through the steps with a concrete example. So let's look at example 1. We have all U.S. voters must have an ID. So this is an all premise. It's going to be the first diagram, which means that, and I'll use this diagram to represent all the U.S. voters. I'm just going to write U.S. voters. So this is the set of U.S. voters. All of them must have an ID, which means this set has to be inside the set of people with IDs. So this says all U.S. voters must have an ID. That's our first premise. Now our second premise is also an all statement. All people who have an ID must be U.S. citizens. So that inner circle is about the U.S. voters. The outer circle is the people who have ID. So this second premise says all the people who have an ID must be U.S. citizens. So this second premise I'm drawing on top of the first premise. And it says all people who have an ID must be U.S. citizens. So I've drawn a diagram that makes my premises true. So this diagram represents premise 1 and premise 2. Let's look at the conclusion. Does this diagram represent the conclusion that all U.S. voters are citizens? And yes, it does, because you notice that the set of U.S. voters is inside the set of U.S. citizens. So it supports my conclusion. It makes my conclusion true. So does this mean it's a valid argument? The argument is valid if all diagrams make the conclusion true. With these particular premises, this is the only diagram that I could possibly draw. And since this diagram, the only diagram that I could possibly draw, makes my conclusion true, my argument is valid. So Euler diagrams, they take a little bit of getting used to, so we're going to do a bunch of different examples in this section so you could see how to use these diagrams. Example 2, all gymnasts are athletes. All dancers are athletes. Therefore, no gymnasts are dancers. Okay, so we have our first premise, which is all gymnasts are athletes. So we're going to put all the gymnasts in the set of all the athletes. So I have my set of gymnasts, and maybe I'll write the whole thing out. That has to be in the set of athletes. So that's our first premise. All dancers are athletes. So notice that says nothing about gymnasts. All it says is the set of dancers has to be inside the set of athletes. So it's possible that, and here I'm going to do this in a different color. It's possible that the set of dancers can overlap the gymnasts. It's possible that the set of dancers can be inside the set of athletes, but around all the gymnasts. It's possible that the set of dancers can be completely inside the set of gymnasts. The only requirement here, one more diagram. What if the set of dancers and the set of gymnasts don't even touch? See, the only requirement for premise 2 is that the set of dancers are inside the set of athletes. It looks like there's 4 possible diagrams that I can draw. So I could draw all 4 diagrams and see if all 4 diagrams make my conclusion true. But oftentimes, if you have a lot of diagrams that you can draw, sometimes maybe we might want to show that it's invalid. Remember, invalid means, can you find one diagram that makes the conclusion false? So the conclusion is no gymnasts are dancers. So that would be this last example I did. That says if this were the dancers, that would make the conclusion true. That does not mean that it's a valid argument. That's just one diagram that makes a conclusion true. So what if I said, okay, here's a set of gymnasts, and I'm just going to write gym. Here's a set of dancers, and here's a set of athletes. Notice that this is a diagram that makes the premises true. So this says all gymnasts are athletes, so the set of gymnasts are inside the set of athletes. All dancers are athletes, so the set of dancers is inside the set of athletes. However, it makes the conclusion false. This says all gymnasts are dancers. The conclusion is no gymnasts are dancers. So since I could draw a diagram that makes the conclusion false, then this is invalid. So remember, valid, all possible diagrams will support your conclusion. Invalid, all you need is one diagram that does not support the conclusion, that does not make the conclusion true. And that's the same as if we were looking at a truth table and we come up with one false. If you just get one false, the argument is invalid. Well, let's do more. All mathematicians are logical. No poets are logical. Therefore, no poets are mathematicians. So here I have my first premise, which is all mathematicians are logical. So the set of mathematicians, so I'm just going to put math, has to be inside the set of logical people. I'll just write logical. So that says all mathematicians are logical. And now that my next premise says no poets are logical. That means the set of poets cannot touch or intersect the set of logical people. So that means I have to put the set of poets outside of the set of logical people. This is the only diagram I can draw for those two premises. And this diagram makes the conclusion true. The conclusion says no poets are mathematicians. Notice that the set of mathematicians and the set of poets, they don't touch, which means this is a valid argument because every possible diagram makes the conclusion. And more. All singers are outgoing. No poets are singers. Therefore, no poets are outgoing. So I have my all singers are outgoing. I have the set of singers, which has to be in the set of outgoing people. Here's my set of singers. And I'm going to draw a big diagram because I already know that I'm going to have possible cases like I did in that previous second example. I'm just going to put outgoing. Okay, no poets are singers. So the only requirement there is that poets cannot touch singers. Notice that that second premise doesn't say anything about being outgoing. So maybe I'll do it in a different color. Maybe I'll do it in yellow. No poets are singers. That means the set of poets can go completely outside. The set of poets can be completely inside the set of outgoing, just not touching singers. That's the only requirement. Or we could have something like this, where the set of poets overlaps the set of outgoing people. So there's three possible diagrams I can draw when I draw that second premise on top of the first one. Well, I don't want to draw all three possible diagrams, so let's see if one of these can make the conclusion false. The conclusion is no poets are outgoing. So what if I went ahead and drew this diagram here for my set of poets? So that's a diagram. It makes all singers are outgoing true, no poets are singers true, and it makes the conclusion no poets are outgoing false, because this says all poets are outgoing. So I've just drawn a diagram that shows that the argument is invalid. Oftentimes when you have a lot of choices on how you can draw your second premise, oftentimes the argument will turn out to be invalid. So might as well just try to come up with a diagram that makes it invalid. If you can't find a diagram that makes it invalid, then it's probably a valid argument, and that means you have to draw all possible diagrams. Example 5, we have all mathematicians are logical, and then we have some poets are logical. So let's look at the set of mathematicians, and I'll just write math. Inside the set of logical, so that says all mathematicians are logical, some poets are logical. So since some poets are logical, the only requirement is that poets overlap logical. And there's a bunch of ways I can draw this. I can do poets overlapping logical but not math. I can draw poets overlapping logical and math. I can draw the set of poets around math, and again overlapping logic. So I got a bunch of ways I can draw that second premise. So instead of drawing all possible diagrams, I'm going to choose the one that makes my conclusion false. So the conclusion would be some poets are mathematicians. So if I drew my set of poets overlapping the set of logical, then this actually says that no poets are mathematicians, and it makes the argument invalid. These last two examples that we're going to look at, they have sets, but they also have single elements. Example 6 says all dolphins love to swim. So that means the set of dolphins has to be inside the set of things that love to swim. Now the second premise says Michael Phelps loves to swim. Michael Phelps is not a set. He's not a circle. He's a dot. He's a single element. So Michael Phelps loves to swim means that, and I'm going to use yellow, that Michael Phelps has to be inside the set of things that love to swim. So I have a choice. I can put Michael Phelps outside of the set of dolphins or inside the set of dolphins. Both would make the premise true. So remember, if you have choices, see if one of those choices will make the conclusion false. So Michael Phelps is a dolphin would mean I would put the dot inside the set of dolphins. But I'm not. I'm going to put Michael Phelps, and I'll just do MP for Michael Phelps. I'm going to put Michael Phelps inside the set of things that love to swim, but outside the set of dolphins. So notice that all dolphins love to swim. True. Michael Phelps loves to swim. True. The conclusion, therefore, Michael Phelps is a dolphin. False. This is invalid. All right, last one. Some Republicans are women. Nancy Pelosi is a woman. Therefore, Nancy Pelosi is not a Republican. Okay. Some Republicans are women means that the set of Republicans, because it's a some are, has to overlap with the set of women. So I'm going to do rep for Republicans and women. That would be my first premise. Second premise, Nancy Pelosi is a woman. Maybe I'll just call her NP. This is similar to example 6. Nancy Pelosi is not a circle. She's a dot. She's a single element. And she's a woman, so I have a choice. I can put her inside the set of women but outside the set of Republican. Or I could put her in the set of Republican and being a woman. I have a choice there. Both of those dots will make that second premise true. So, I'm going to look at the conclusion. Nancy Pelosi is not a Republican. And I'm going to choose to make this diagram. And here's my Nancy Pelosi. So, some Republicans are women. True. Nancy Pelosi is a woman. True. She's in the set of women. Therefore, Nancy Pelosi is not a Republican. False. This diagram makes the conclusion false. This is invalid. And that's all we're doing in this section. We're just trying to draw diagrams to represent our quantified arguments and then show valid or invalid by a picture, not a truth table. And that's it for chapter 3.